You are looking at a number that did not exist a year ago, 276 gigapascals. That is the hardness rating a Chinese lab just gave a diamond it built from scratch in a lab, more than double what a natural diamond can hit on its best day. But here's the part almost nobody connected. 1 month before that number went public, China's government banned the sale of diamond like it to America outright. The record and the restriction landed back-to-back in the same news cycle, and once you see why, the timing stops looking like an accident. Start with the ban, because the ban came first. On December 2, 2024, the U.S. Commerce Department added 140 Chinese companies to its entity list, a roster of firms that American suppliers need special permission to sell to. Most of the names on that list build chips or the machines that make chips. It was, at the time, the broadest single round of chip sanctions Washington had ever issued against Chinese industry in one move. Nearly every company on that list was based in China or Chinese-owned, and the new rules specifically tightened controls on the equipment and software needed to build the most advanced chips, plus the high-bandwidth memory that powers AI accelerators. Washington had rolled out earlier rounds of these restrictions going back to October of 2022, when the first sweeping controls targeted advanced AI processors and chip-making tools directly. December 2024 was the point where Beijing stopped absorbing those rounds quietly. China did not wait. The next day, its Commerce Ministry announced it was banning the export of gallium, germanium, and antimony to the United States, three materials American semiconductor and defense manufacturers depend on and barely produce at home. Those three weren't a fresh idea either. China had already required special export licenses for gallium and germanium back in July of 2023, and added antimony to that licensing regime in August of 2024. December 2024 was the point where licensing turned into an outright ban, aimed at one country specifically. That part of the story got most of the headlines, and it deserved them. But buried in the same announcement, one line down from gallium and germanium, sat a category almost nobody outside the materials industry had heard of. Superhard materials. Diamond, and the synthetic compounds built to behave like it. You would be forgiven for skimming past that line. Diamond sounds like jewelry, like engagement rings and watch faces, not something that shows up in an export control filing next to the metals inside a missile guidance system. But industrial diamond has almost nothing to do with rings, and only a small slice of what China produces is even gem quality to begin with. It shows up in saw blades that cut concrete, in the drill bits that bore through rock a mile underground, in the polishing compounds that finish a jet turbine blade to a tolerance a human hand could never hit, and in the ultra-thin wire that slices raw silicon ingots into the wafers every chip and solar panel on Earth gets built from. Anywhere something has to cut, grind, or polish. Something almost as hard as itself, diamond, or a synthetic material built to outperform it, is usually the tool doing the work. Take that tool off the shelf and you do not stop the ring industry. You slow down machining, drilling, semiconductor fabrication, and defense manufacturing all at once, because they all quietly lean on the same handful of super hard abrasives. Most of that supply gets made two ways: high pressure, high temperature synthesis, often shortened to HPHT, squeezes carbon under crushing pressure and heat until it crystallizes into diamond. The same basic conditions diamond forms under naturally, just compressed into a machine instead of the Earth's mantle. Chemical vapor deposition, or CVD, builds diamond up more slowly, layer by layer, from a carbon-rich gas inside a chamber, which lets manufacturers grow larger, more electronically useful diamond wafers for advanced applications. China dominates the first method almost completely and is rapidly closing the gap on the second, which is exactly the kind of two-front lead that turns a manufacturing advantage into a choke point. That is what made the December ban different from a symbolic gesture. It was not aimed at consumers. It was aimed at the tools other industries use to build everything else. The specific language China's Commerce Ministry used was that these materials had dual military and civilian uses. The same justification applied to gallium and germanium, and the ban sat inside a broader update to China's dual-use export control list, the legal framework Beijing now runs almost all of its trade retaliation through. Analysts covering the move at the time flagged tungsten as a likely next target on that same list. They were right, and it didn't take long to prove it. On February 4, 2025, barely 2 months after the Superhard materials ban and 1 month after the diamond record, China's Commerce Ministry announced fresh export controls covering tungsten, tellurium, bismuth, molybdenum, and indium, requiring special permits for shipments of each. Tungsten alone matters enormously here, since China controlled roughly 80% of global tungsten production going into that announcement, and tungsten carbide happens to be one of the other main materials cutting tool manufacturers reach for when diamond isn't hard enough or heat-resistant enough for the job. Superhard materials weren't a one-off. They were the opening move in a pattern that kept running for a year afterward. The restriction went further than just the finished material, too. The same licensing rules China had already put in place that August extended to the smelting and separation technology and the specialized machinery used to process superhard compounds in the first place, not just the compounds themselves. That distinction matters more than it sounds like it should. Banning a finished product still leaves a buyer able to shop around for a different supplier somewhere else, but restricting the equipment and process knowledge behind it is slower, deeper leverage. It targets the part of the supply chain that took decades to build, the kind that can't be replicated by writing a bigger check. Enforcement got sharper at the same time. Alongside the ban, China's new rules required exporters to disclose exactly who the end users of their shipments are, a change specifically meant to make it harder for controlled materials to reach the United States through a middleman in a third country. That single change closes one of the oldest tricks in trade sanctions, routing a restricted shipment through a friendlier buyer first and letting it quietly find its way to the actual customer afterward. It does not close it completely, but it raises the cost and the paperwork trail for anyone trying. None of this happened in a vacuum either. Trace the timeline back further and you find a country slowly working through almost every material category the American tech industry depends on and doesn't produce enough of itself. Gallium and germanium in July of 2023. Antimony in August of 2024. Superhard materials and a graphite review in December of 2024. 7 more rare earth elements added to the same control list months later. Each move on its own reads like a narrow technical trade dispute. Stacked together in order, it reads like a country working down a checklist. And then a month later, the record landed. On January 3, 2025, a research paper went live in the journal Nature Synthesis. The team behind it worked out of Yanshan University in the northern Chinese city of Xinhuangdao, led by a materials scientist named Tian Yongzhen, alongside collaborators from Nanjing University of Science and Technology and Ningbo University. Their paper described a new kind of lab-grown diamond built from ultrafine nanocrystalline twinned crystal structures with an average grain size of just 18 nanometers and twin boundaries spaced only 2.3 nanometers apart. And when they measured its hardness on the Vickers scale, the standard industrial test for how much force a material resists before it deforms, it came back at 276 gigapascals. A quick note on what that test actually measures, since the number means nothing without it. Vickers hardness works by pressing a tiny diamond-tip pyramid into the surface of a material under a controlled load, then measuring the size of the indent it leaves behind. A softer material dents easily and leaves a large mark. A harder material barely dents at all. Run the math on how much force it took to leave that barely there mark, and you get the Vickers number expressed in gigapascals, a unit of pressure so large that Earth's atmosphere at sea level only registers around 0.0001 of 1 gigapascal. To generate that same 276 gigapascals of pressure without a lab, you'd need to concentrate the entire weight of a fully loaded cargo ship down onto an area the size of a fingernail. To put that number where it belongs, a natural single crystal diamond, the kind pulled out of the ground, tests between 60 and 120 gigapascals depending on which direction you're cutting into the crystal, because a single crystal isn't uniformly strong in every direction. The Yanshan material more than doubled the high end of that range. It set a new world record for the hardest material ever measured, and it did it 11 years after the last major jump in that same lab's own numbers. The mechanism behind that number comes down to how the crystal itself gets built, and it's worth walking through because harder diamond sounds like marketing until you see the structure underneath it. Diamond gets its strength from a rigid lattice of carbon atoms locked into a repeating crystal pattern. In a natural diamond, that lattice tends to form as one large, continuous crystal, and a single large crystal has weak points, because a crack or a dislocation can travel cleanly through uninterrupted material. The Yanshan team did not grow one big crystal. They grew the diamond as an enormous number of nanoscale grains, each one twinned, meaning the crystal structure flips its orientation at repeating internal boundaries like a stack of mirrored panes. Every one of those twin boundaries acts as a wall a crack has to fight through before it can keep spreading. Materials scientists have a name for this general principle, the Hall-Petch effect, the observation that shrinking a material's internal grain size tends to increase its strength because more grain boundaries mean more obstacles standing between a crack and the rest of the material. Diamond researchers had been chasing that principle for years, but nobody had managed to fabricate a nano-twin diamond structure directly from carbon at scale until Tian's lab cracked the process. Shrink the grains small enough and pack in enough of those internal walls, and you get a material where fractures run out of room to travel before they've done any real damage. The result is chemically the exact same carbon that sits in an engagement ring, just structured so a crack has nowhere to run. A record like this doesn't stay academic for long either. The research paper itself points toward exactly the kind of high-end industrial and scientific use cases you'd expect from a material this hard. Precision cutting tools that hold an edge through jobs that would grind ordinary diamond tooling down. Ultrafine polishing heads for semiconductor wafer production, where even a few nanometers of surface roughness can ruin an entire chip. Diagnostic and quantum sensing equipment, where diamond's crystal structure already plays a role and a harder, more defect-resistant version opens doors that weren't there before. None of that shows up on shelves next season. Lab-scale breakthroughs like this one typically take years to move from a research paper into a production line, and scaling nano-twin diamond blocks up from lab samples to industrial quantities is its own unsolved engineering problem, one the 2014 version of this same material never fully cleared for mass manufacturing. But the direction is set, and the country doing the setting is the same one that just told America it can't buy the raw material this whole category depends on. If you're finding this breakdown useful, go ahead and hit subscribe now. This channel covers the technologies and materials science coming out of China that most Western coverage skips past in a single sentence, and there's a lot more of it coming. This also was not Yanshan's first record, and it wasn't even the lab's first superhard material to make international headlines. In 2021, the same research group announced AM33, a carbon-based glass rated at 113 gigapascals on the Vickers scale, hard enough to scratch a natural diamond even though it isn't diamond at all, and tough enough, by the researchers' own estimate, to build bulletproof windows 20 to 100 times more resistant than versions already on the market. That material started as fullerene, a different carbon structure pressed at 25 gigapascals and 1200 degrees Celsius over a slow, carefully controlled 12-hour cycle. This is a lab with a track record of breaking its own records, not a one-time headline. Go back further to 2014, and the same lab under the same lead scientist published a diamond breakthrough in the journal Nature that stunned materials researchers at the time. That version started with carbon onions, spherical nanoparticles made of concentric layers of carbon nested inside each other like carbon versions of Russian dolls. The team compressed those carbon onions under roughly 20 gigapascals of pressure at 2,000 degrees Celsius, hundreds of thousands of times normal atmospheric pressure, and forced them to reorganize directly into a nano-twin diamond structure. That material hit a Vickers hardness of around 200 gigapascals and stayed thermally stable at temperatures over 200 degrees Celsius higher than natural diamond can handle before it starts to oxidize and burn away. For a decade, that 2014 material held as close to an unbreakable ceiling as the field had. The 2025 paper cleared that ceiling by 76 gigapascals, using a refined version of the same twinning principle, tuned down to an even smaller grain size. So why does a lab record in Xinhuangdao matter to anyone outside a materials science journal? Because China backs those papers with the factories that actually manufacture almost all of the world's superhard material. According to the U.S. Geological Survey's own minerals summary, China led global production of synthetic industrial diamond as of the most recent published data, with the United States, Russia, Ireland, and South Africa rounding out the top 5 producers. Together, those 5 countries account for roughly 99% of the world's synthetic industrial diamond supply, out of more than 15.4 billion carats produced worldwide in a single year. China sits at the top of that list by a wide margin, and it isn't close. How wide, exactly, is genuinely disputed, and it's worth being honest about that instead of reaching for the biggest scary number available. Some industry write-ups have claimed China controls as much as 95% of global synthetic diamond output, a figure independent trade analysts have pushed back on as too high once you account for domestic production in the US, Russia, and elsewhere. A more careful estimate comes from tracking a single Chinese manufacturing hub, Zhejiang County, a cluster of factories that alone produces an estimated 25 to 40% of the entire world's synthetic diamond supply, exporting to more than 50 countries from a handful of square kilometers where the raw carbon suppliers, the high-pressure press manufacturers, and the polishing workshops all sit within walking distance of each other. Locals call it Diamond City, and the branding isn't subtle. The streetlights along the main roads are shaped like cut diamonds, and the town's trading center advertises itself as the place where the raw material for the rest of the world's cutting tools changes hands. That kind of clustering is its own advantage, separate from raw output. When every supplier a factory needs sits a few minutes away by truck, the cost of building one more press, training one more polisher, or scaling up one more production line drops, in a way a competitor spread across a whole country can't easily match. It's the same logic that turned a stretch of California into the default location for chip design decades ago, just applied to compressing carbon instead of etching silicon. And the pipeline behind that output keeps getting deeper. China also builds most of the high-pressure presses those factories run on, the machines that generate the crushing conditions synthetic diamond needs to form in the first place, so the country supplies both the finished material and the equipment that makes it. Whichever percentage you land on, the takeaway doesn't change. One country, and often one industrial cluster inside that country, makes most of the material the rest of the world's cutting tools depend on, and the United States imports a meaningful share of what it uses. In 2021 alone, the US imported roughly 192 million carats of synthetic diamond from China, and domestic American production, spread mostly across a handful of specialty manufacturers, has never come close to replacing that volume on its own. Now put the two halves of this story back together. China holds the manufacturing base for the material. China's own labs just reset the world record for how hard that material can be made. And China's government, in the same week it was retaliating against American chip sanctions, chose Superhard materials as one of exactly 4 categories to restrict from US buyers, alongside gallium, germanium, and antimony. That is not a coincidence of timing. That's a country cutting off access to a material right as its own scientists prove they can make a better version of it than anyone else on Earth, and it's worth knowing whose money built that lab result in the first place. The 276 gigapascal paper credits funding from China's National Natural Science Foundation, the country's national key research and development program, and a provincial science foundation in Hebei, the province where Yanshan University sits. This wasn't a scientist tinkering on a weekend grant. It was a state-funded materials program inside a state-funded university, delivering a headline result on the exact same material category the government had just restricted. None of this means American industry grinds to a halt overnight. The ban applies specifically to direct exports to the United States, and diamond tooling made in China can and often does still reach American buyers indirectly through third countries or finished products assembled elsewhere. Export bans like this one are messy and porous in practice, rarely a clean, instant blockade, and every extra step in a supply chain still adds cost, adds delay, and adds a country in between that has its own interests. For an industry that has spent decades assuming Chinese-made Superhard tooling would just keep showing up on schedule, even a partial disruption forces a scramble that didn't exist 18 months ago. It also raises a question. American manufacturing has mostly avoided asking out loud what happens to precision machining, semiconductor fabrication, and advanced tooling in the US if the country that makes almost all the world's Superhard abrasives decides access is a privilege instead of a given. The materials themselves aren't rare in the way that, say, a specific rare earth element is rare. Diamond is, chemically speaking, just carbon, one of the most common elements on the planet. The scarcity here isn't geological, it's industrial. Decades of manufacturing investment landed in Chinese factories, presses, and polishing workshops instead of American ones, quietly over 30 years, while nobody in Washington was treating diamond tooling as a strategic material worth protecting. That concentration is now doing exactly what concentrated supply chains always eventually do in a trade war. It's becoming leverage. American companies aren't sitting still, to be fair. A handful of specialty manufacturers in the US already produce CVD diamond for high-end electronics and defense applications, and there's real investment flowing into expanding that domestic base since the ban landed. But building a competing HPHT press industry, from the raw carbon sourcing to the polishing infrastructure to the trained workforce running it, is a decade-scale project, not a response to one bad quarter. China spent 30 years building the cluster in Zhejiang. Nobody replicates that with a single round of tariffs or a single government grant, and every year that domestic build-out takes to mature is another year U.S. buyers stay exposed to whatever Beijing decides to restrict next. And leverage built from a material is only as strong as how much of it you actually control. Diamond, it turns out, is one of the smaller chips on the table. China's real advantage sits somewhere else entirely, buried under a discovery announced with far less fanfare than a hardness record and worth more than every synthetic diamond factory in Zhejiang combined. That story starts underground,